Alright, so this is the second video for section 6.1 in AP Calculus, and today we're actually going to start talking about slope fields, what they are, how you make them, that sort of thing. So, for example here, if I was to solve this solution, or solve this differential equation, just like we did yesterday, I would integrate both sides here. So the integral of dy dx would just be y. The integral of 3x would be 3 halves x squared. Hopefully you're kind of quick at that. The integral of negative 3 would be negative 3x. And then, of course, I wouldn't want to forget my plus c. So that means that all functions that have 3 halves x squared minus 3x and then any sort of constant stuck on the end of them, their derivative is 3x minus 3. So the directions here are to graph the whole family of functions that would solve this differential equation. So that means that I could put any constant I want right here, and that function would be a member of this family of functions. Now, does that mean that I want to have to put every possible constant in the world and draw that graph? Absolutely not. So here's where your graphing calculator comes in handy. So pause the video if you need to for a second and get that out, because I'm about to show you how to do this on your graphing calculator. Okay, so I'm going to open up my calculator, and the first thing that you're going to do is you're going to go to your Stat Edit menu. And in L1, I want you to type all the integers from negative 3 to positive 3. And those are really just arbitrary values, but those numbers are now going to be my plus c's, my different constants. So I could put any amount of numbers I want to in there, but that's going to give me 7 different constants to use. Now, does that mean that I'm going to have to go and type in 7 different times that function? No. So now you go to your y equals, and you type in your function. You're going to type in 3 halves x squared minus 3x plus, and then you're going to get to the c. You're not going to put c, you're going to put L1, because that's where we just typed those numbers in. So if you look right above your 1, you see mine's in blue, but you should see a little L1. So press second 1, and look at that. It puts L1 in for us. Now hit zoom 6. Mine's thinking. So there's the first function. There's the second. Mine is being super slow. There's the third. But you're going to get a total of 7 different graphs that all have 3x minus 3 as their derivative. So this is the one using negative 3 as the constant, negative 2, negative 1, 0, 1, and then the next 2 will be 2 and 3. So all those functions right there have a derivative of 3x minus 3. So no, that's not all the functions in the world, but it's a good chunk of them. It's 7 of them. So it gives me a good idea of what they look like and where exactly they would be graphed. And notice that they're all along that line x equals 1, because they all share that x coordinate for their vertex. So you know that all the parabolas with that width and stuff, just translated up and down, would have a derivative of 3x minus 3. So there you go. So I want you to pause the video for a minute, and I want you to give it a try with this one. You're going to have to integrate it first, and then graph the family of functions. Okay, so hopefully when you integrated it, you got negative cosine of x plus e to the negative x plus 2x to the 4th plus c. And then when you typed it in your calculator, you could have kept those same 7 numbers in L1, and then of course when you type it in, you would have just put an L1 in place of the c. And this should be the 7 graphs that you got. So the next thing I want to talk about is, what if you had to draw the slope field yourself? So suppose we wanted to graph that 3x minus 3, dy dx equals 3x minus 3, without actually integrating it and solving it. Since the differential equation, what a derivative gives us, which we've been saying for months, is the derivative gives us the slope at any point on the function. We can use that piece of information to draw just a small piece of the linearization of the function at a particular point. And repeating that process over and over produces what is known as a slope field. So I want to construct a slope field for dy dx equals 3x minus 3. So what I'm going to do is we're going to calculate the slope at every integer point on this graph. And notice we're doing a very small interval, just from -2 to 2. We're basically going to do it at every single one of these corners on my graph. So even though it's a small area, I'm going to end up doing 25 different points by the time I'm done. So all you would do is you would pick a point. So the coordinates of this point, for example, are -2, +2. I would take that point and I would substitute it into my differential equation to find the slope there. So if I'm at -2, +2, that means that x is -2. So 3 times -2 would be -6, minus 3 is -9. So at this particular point, the slope of my original function would be -9. Now, am I necessarily going to be able to draw an exact slope of -9? No. But what I do know is that it's a pretty steep slope, and it's negative. So that's what I'm going to draw right there. And then I'm going to repeat that for this point, which is at -2, +1. Substitute in, I get -9 again. So I'm going to make sure that when I draw it, it looks pretty much just like the one I just did. And you might be figuring out that all of these points that have -2 for the x coordinate will have a slope of -9, because the y coordinate isn't involved in this formula at all for this particular problem. If there had been some y's in here, then I would need to include it. So then you'll do it again for all of them with an x coordinate of -1. If I substitute in -1, I get -3 minus 3 is -6. So -6 is still a pretty steep negative slope. But it's not quite as steep as the one I've already drawn. So when I draw it, I'm just going to make sure that it's not quite as steep as the ones that I drew at -2. Kind of like that. Okay, so I want you to pause the video now and see if you can finish off for x is 0, x is 1, and x is 2. Okay, so check yours with mine, and it may not look exactly like mine, but notice I labeled mine up here at the top, which is great for you to do too, especially if it's a whole column or whole row that has the same slope. So you should have got -3 for all the slopes when x is 0, 0 for all the slopes when x is 1, and 3 for all the slopes when x is 2. So now I'm sure you can appreciate why we're not going to do this for -10 to +10. We would be here all day doing this one problem. And the thing that I don't like about constructing the slope fields ourselves is that it's very subjective, because these slopes, I mean, that's not exactly -3. We're just kind of estimating it in there. So one of the more common things that you're going to be asked to do is you're actually going to be given some graphs of some slope fields, and you're going to be given some differential equations, and you're going to have to try to match them up. And we're actually going to play a matching game in a few days with all this stuff. So here, without a calculator, I've got these 4 differential equations and these 4 slope fields, and I want to try to match them up. So I want you to pause the video for a minute and kind of play this game with yourself. See if you can figure out what goes with what. Try plugging in some points and figuring it out. Okay, so I got BDAC. And the way I figured this out was, okay, looking at the first one, I have x minus y. So that means that at every single point, if I take the x coordinate minus the y coordinate, that would give me the slope here. So some things to think about are, okay, well, if x is bigger than y, I'm going to have a positive slope. If x is smaller than y, I'm going to have a negative slope. And if they're equal, I'm going to have no slope. So look here, for example, where x and y are equal at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Do you see how you have those straight slopes there at -1, -1, all that sort of thing? Those match up. So that's how I kind of figured that one out. And then also look here. When I have bigger y coordinates, so for example, this point, let's say that it's 1, 3. X is smaller than y. 1 minus 3 would be -2. That's a logical assumption for that to be a slope of -2. And you could try it over here where x is bigger than y as well. Then for number 2, I said that it was d, x times y. So I know a couple things about that. First off, if either one of those coordinates is 0, my slope's going to be 0. So those coordinates are 0 on the y-axis, and notice all those slopes are 0. And then also on the x-axis, and even though we can't see it, you can tell by what's coming towards it that these slopes are also approaching 0. Another thing is that when both of these are positive, we're going to have positive slopes. They're both positive in the first quadrant. Do you notice how every single slope drawn here is positive? If one of these is negative, then we're going to have negative slopes. So that would be over here. All these slopes are negative, as well as over here. And if they're both negative, negative times a negative would be a positive slope, which happens in this quadrant. So that's D. So you're really not calculating any slopes. You're just kind of playing the guess and check, kind of figuring out patterns games. And then the same thing with A and C. With number 3, I said that it was A because when you have x over y, first off, anytime x is 0, the slope's going to be 0. Well, x is 0 on the y-axis. So there's another one that has no slope on the y-axis, which goes along with D, but there's some things that make these separate. Also, whenever x is bigger than y, I'm going to have a steeper slope. For example, 2 over 1. So at 2, 1, I would have a steep slope. Whereas at 1 over 2, my slope is not as steep over here. So you can match it up that way. And then on number 4, 4 is similar to 3, except here I have no slope when y is 0. So that would be all along the x-axis. And even though you can't see it, do you see how the slopes that are close to the x-axis are pretty close to being flat? And then they're going to be undefined when x is 0. You can't see it real well, but do you see how they've got, you can kind of see, they've got some vertical lines here. Remember, vertical lines have a slope of 0? So we've got vertical lines here. And then going back to this one from number 3, you see how these slopes are making vertical lines here when y is 0? So kind of a little bit of a matching game for you. I think it's kind of fun. It's kind of like a puzzle. And come to class with any questions if you have it from today's video.